My name is Sarah Hall, and I'm a geoscience professor at College of the Atlantic. I've been working with the All About Arsenic project during the last few years, building aspects of the project into activities with my college students. In this talk, I'm going to tell you about a spin-off project funded by an NIH SEPA supplement grant that I've been working on with students through independent study projects, summer internships, and also with collaborators at MDIBL, Dartmouth College, and many community members. Currently, we're in the middle of a monthly private well water monitoring survey in an effort to view temporal patterns in local water quality. The bedrock of New England is a known source of arsenic in the groundwater throughout the region, as illustrated in the maps here on the right, with about half of the residents in Maine and in New Hampshire relying on private well water for their drinking water, a water source that is not regulated by national or state legislation. This is an important public health issue for the region. New England has a shared deep history that has resulted in the assemblage of our fractured arsenic-bearing bedrock, a modification of a classic textbook drawing of the last billion years of the North American continent's eastern margin history is shown in the figure on the right, with highlights in red where arsenic-bearing rocks enter the story. Today, the many bedrock fractures remaining from the mountain building events enable groundwater storage, flow, and extraction from otherwise fairly impermeable bedrock. Another known source of arsenic in New England and throughout the U.S. is related to the widespread application of pesticides on agricultural fields throughout the 20th century. The map on the right here shows an estimation of the spatial distribution of arsenic-bearing pesticides used on croplands throughout New England, with the darker colors representing a higher likelihood of pesticide use. In Maine, private wells can be drilled deep into fractured bedrock, like this one, or drilled shallower into superficial deposits, such as gravel or sand that were deposited during recent glaciations, or else shallow dug or driven wells that would be just in the upper 10 feet of the surface or so. There is a worry that the shallow wells, or wells that are sourced by near-surface waters, can be contaminated with arsenic through the mobilization of the residual pesticide artifacts in the soils. Further, more and more drilled wells that tap arsenic-bearing rocks are coming online in recent years as drilling technology improves and people are living in rural areas. Overall, there has been a fairly high risk of exposure to chronic, low doses of arsenic via drinking water here in Maine for decades, and that risk remains. Thanks to data available through the Maine tracking network of the Maine CDC, we can spatially view well water quality and public health data together. The map on the left here shows the percent of homes with private well water by county, with this red area showing locations where over 68% of residents rely on wells. The center map here shows testing behavior for arsenic by town, with the darker red colors showing locations of the higher numbers of tests. Areas in white are locations with no data. Notice how easternmost Maine has very low test results for arsenic, yet high reliance on well water and a history of arsenical pesticide use. Considering this, additional local high-resolution studies are warranted in Maine, especially for the Down East coastal region. This current study is focused on Mount Desert Island, the area shown in this black box. Zooming into this region, we can see that the bedrock is a mixture of intrusive igneous rocks that are in pink and purple, metasedimentary rocks in light blue and green, and that the region is dissected by northeast-southwest trending faults. During 2016 to 2019, we conducted a study to investigate how the spatial pattern of groundwater chemistry compares to bedrock type and geologic structure location in this region. We had 150 well owners volunteer to be part of the study of the northern MDI region. We generally found that arsenic is associated with the metasedimentary rocks, those in green, and that higher uranium, is associated with the igneous rocks in pink. In the interest of time, I'll let you visit my student Gabby Moreau's poster at this conference, showing some of the maps that have the results of our spatial study. But from this data set that we collected during these 3 years, other questions came up based on the participant data. For example, some of the people who volunteered in this study already knew they had arsenic in their water, and they had a treatment system in place. And in this case, we sampled both the unfiltered water, shown in orange here, and the filtered water, shown in blue. The red arrow indicates the Maine maximum contaminant level for arsenic, which is 10 parts per billion. And as you can see, some of the filters are working better than others. In fact, one filter actually added arsenic to the water. As we talked with participants, and in some cases also got a tour of their water system, we gathered a lot of anecdotal information highlighting the need for future studies. How well do filtration systems work? Do people understand how to maintain their filtration systems? And how do private well water owners use these data once we give them their results? We heard from some well owners that their wells tend to run dry in late summer, or that their filter filled up faster at different points of the year. Some well owners mentioned that they have noticed changes in well yield over the years since the installation of their well. Comments like these made us wonder how the abundances of elements change through time, or if there's a seasonality to the water chemistry in this region. According to the Coastal Maine Climate Futures document issued by the Climate Change Institute of UMaine, coastal Maine can expect an extended growing season, extreme precipitation events, and heat waves and droughts due to climate change. Coastal communities can expect reduced groundwater levels and stream flow. So with 50% of Mainers and 80% of Hancock County residents relying on unregulated private well water, and given these future climate change scenarios, we decided to focus on the question of temporal changes in well water quality. Indeed, there's a growing body of literature on this topic because Maine is certainly not the only location facing these modern and future threats. Other studies have shown arsenic to vary in wells due to a number of reasons, either directly or indirectly related to changing water level and flow rate. Since most of the data collected during 2016 to 2019 for our spatial study was collected during December to February, which is typically the wetter part of the year, we plan to resample all of the wells in the dry season. So when is the dry season for Mount Desert Island, Trenton area? Well, stream gauge data can give us a view of the annual flow patterns of surface water. The USGS Otter Creek gauge on Mount Desert Island shows lowest surface water levels occurring in latest August and earliest September. We can locate the dry season in the binned 15-day precipitation data with the driest months of August through October, here indicated by these brown bars. We have 2 USGS groundwater wells on Mount Desert Island, but regular monitoring of both were discontinued in 2019. But the data for both wells going back through 2015 is shown here. The orange line shows groundwater levels from a deep, low elevation well, while the green line shows the water level in a similarly deep, high elevation well. The higher elevation well sees more variability in water level throughout the year and tends to reach its lowest water levels nearly a month later than the shallow wells. So while the streams and the wells that are likely fed by shallower groundwater tend to reach their lowest levels in late August or early September, the higher elevation or groundwater wells fed mainly by deeper water seem to reach their lowest levels later in October. We conducted a reconnaissance sampling event in latest September, early October for a few of the wells from the original study. So on this plot, I'm showing the arsenic concentrations in these reconnaissance wells with the dry season values in orange and the wet season in blue. I've indicated the 10 parts per billion line and 5 parts per billion limits here, which are the Maine and the New Hampshire maximum contaminant levels, respectively. Notice that in some cases, like in well O, for example, if the well owners tested their well in the wet season, they would not get any indication from the state that their water exceeds the MCL, because here their arsenic level is only 8.5. But if they had tested during the dry season, they would get information from the state that it exceeds the MCL because their level was 17.5 parts per billion. So these changes overall are not huge, but they matter for well owner awareness. In fact, well E was a well that has particularly high arsenic level to begin with, at 250 or so parts per billion, yielded a dry season value of over 700 parts per billion, more than double the wet season value. The owner then tested a month later after changing the particulate filter and reported that the arsenic level was back down in the 200s. So was this a high arsenic value due to seasonality effects, or dirty filter, or a combination of both? We don't know. Due to COVID-19, we were unable to plan for a large dry season sampling event where student researchers and I would enter homes and collect samples. Instead, the students designed a contact-free sampling strategy focusing on a set of wells every month for 1 year. We began this effort in July 2020 and we're currently in progress. We chose 30 wells to sample monthly based on their arsenic and uranium concentrations, as the spatial study suggested that our metasedimentary bedrock tends to supply arsenic, while our granitic bedrock tends to supply uranium, both potential contaminants. We specifically targeted wells with arsenic levels around the Maine MCL, ranging from about 1 to 60 parts per billion. We sample the wells at the end of every month, usually the 28th or 29th day. For every water sample, we analyzed 13 elements shown along the x-axis of the bottom graph. With 8 months of data, we're starting to be able to see the chemical signature for each well, as an example, as one is shown here. The largest monthly changes typically are in manganese and iron. Our initial question was really focused on arsenic abundance during the dry season compared to the wet season. While some wells are quite consistent, varying only 1 to 2 parts per billion overall, Others show a pattern of either increasing or decreasing arsenic through the dry season, and still others reveal variations of 20 to 30 parts per billion during the testing period. For example, N1 here has an arsenic concentration that fluctuated above and below the MCL throughout the last 8 months, with a range of about 20 parts per billion, as you can see, between August and November. On shorter timescales, we see arsenic concentrations vary pre- and post-rain events. At this point, rain event sampling has just been opportunistic and exploratory. So far, we've only conducted 2 rounds during large rain events near the 1st of November and the 1st of March. Many wells show increases in arsenic post-rain. For well N1, the concentration doubled from 16 to 32 parts per billion between February 27th and March 2nd. And as you can see, 32 parts per billion here is higher than any other value measured in this well during the regular monthly sampling. So the picture that is forming from these data so far is that wells have their own unique situation, each well. Therefore, I'm going to just focus on a few examples for the remainder of the talk to highlight some emerging well stories. Some of the wells, such as 2 that are shown here, have fairly consistent arsenic values that fall between the Maine and the New Hampshire MCL. In these plots, time is on the x-axis and arsenic concentration is on the y-axis, and they both are between 0 and 10 parts per billion. Both of these well owners see no reason to further filter their water, as arsenic values fall below the Maine MCL. Here are similar plots for 2 other wells in this study. In both cases, the owner was not aware that they had high arsenic levels in their well, or was not aware that it was something to be concerned about at the reported levels. In 2016, we found that both wells had arsenic levels above the Maine MCL, and after receiving some information about chronic arsenic exposure and mitigation options, both owners installed a reverse osmosis system. We continue to sample both wells monthly, collecting both a pre- and a post-filter sample. And you can see the filtration is working well, with the filtered samples in blue here all nearly 0 arsenic. Note that the arsenic levels in the unfiltered samples, these orange dots, vary around 5 parts per billion or so over the sampling period. Well U is similar to the last 2 wells. The owner installed a point-of-use reverse osmosis system following the 2016 study. And we continue to sample pre- and post-filter. Earlier this year, we noticed that their filtered water had the same arsenic value as their unfiltered water. I alerted them to this issue, they changed the filter, and their arsenic levels went back down. So this highlights an issue that not only are filtration systems dependent on well owner knowledge and understanding of the maintenance needed, but also that the timing of maintenance might fluctuate due to changing water chemistry or water use. Some wells in our study have low arsenic values, but may have other elements of concern. Well J, shown here, has notably high uranium levels, the highest by an order of magnitude in all the wells of the study. I suggested having their water also tested for radon, which the owner did, and remediation was recommended. The radon removal bubbler system shown here requires a large insulated space, and it tends to make a lot of noise when it runs. The homeowner does not have a full basement, but rather a crawl space that this setup will not fit within. So the consultant told them that they should consider building another insulated room onto their house to accommodate the system. Clearly, the situation was much more complicated than the well owner had planned for. For some well owners, there are many friction points that make it hard for them to improve their water quality, despite an interest in and a desire to do so. Many of the wells in this study are located on properties that are either current or previous agricultural lands. We've begun to collect both soil samples and rain event samples, especially at locations that have dug wells. In this location, well BB1, shown in green, is a drilled bedrock well, and well BB2 is a dug well located nearby. The property resides in an area of high likelihood of prior arsenical pesticide use. Arsenic was found in both soil sample pits, S1 and S2, and we see increases in arsenic in the dug well after rain events during both seasons. Overall, the preliminary data from this study confirms findings of other studies on the topic, that elemental abundances in well water do vary throughout the year, and that these variations are likely due to changes in local flow conditions related to many things: seasonality, weather events, water use, and water system infrastructure and maintenance. We're beginning to see the unique patterns of elemental abundances for each well, which are likely characteristic of the dominant water source for each well, deep or shallow. The main take-home point for me is that each well is a unique physical situation related to location characteristics, but also a social situation in that the water quality depends on the well owner's understanding of their system and their ability to interact with it. My collaborator Jane Disney refers to this as the unique well story, incorporating the natural and the human influences on personal drinking water quality.